For this question, we want to find all vertical asymptotes and create a rough sketch of the graph near each asymptote. The function we have is f of x equals 4 over x plus 3. The way we find vertical asymptotes is that we first need to make sure that our function has no common factors. Our numerator is already factored, and our denominator is already factored. And there are no common factors between the numerator and denominator. No common factors tells us that there are no holes or removable discontinuities for this particular rational function. So no common factors tells us that there is no hole in the graph, and sometimes we call those holes in the graph removable discontinuities. So now that we know that there are no holes and no removable discontinuities, we can find the vertical asymptotes by setting our denominator equal to 0. So I set the denominator equal to 0, subtract 3, and I get the solution of x equals -3. This is going to be the location of our vertical asymptote. So this rational function has a vertical asymptote at x equals -3. Now I want to think back to what the definition of a vertical asymptote is so that I can think about what the graph looks like around that asymptote. The definition of a vertical asymptote says that as x is approaching a particular value, then y is either approaching infinity or -infinity. So I know that as my x gets closer to, that should be -3, then my y is either going to approach positive infinity or -infinity. And so that's what I need to figure out when I'm drawing my rough sketch of the graph near that asymptote, is whether my y will approach infinity or -infinity. So as I start to sketch, my vertical asymptote is at -3, so I'm going to draw a vertical dashed line to represent the location of that vertical asymptote. And then I need to figure out what is happening on either side. So to the left of that -3, we call that -3 with a minus as the exponent, as a superscript. And that means that we're talking about values that are less than -3. And then if we think about the right of -3, that's -3 with a plus as the superscript. Those are numbers that are larger than -3. So if I choose a number that is close to -3, then I'll be able to tell whether the y is going to infinity or -infinity. So as x approaches -3 from below, I'm going to pick a number that's smaller than -3, like I'm going to choose x equals -3.1. This is a number that's smaller than -3. And I'll substitute that into my function and see what happens with the y value. That's 4 over -3.1 plus 3. That's 4 over -0.1. And that's going to give me a negative value. And so that tells me that for the lower side, the y is going to go to -infinity. So that tells me that the graph will look something like this. And notice I'm on the left side of -3, the lower side of -3, and I'm drawing my y to go to negative infinity because this came out to be negative. And then as x approaches -3 from above -3, I would choose a number like -2.9. That's something that's a little bit bigger than -3. If I substitute that in my function, that would be 4 over -2.9 plus 3. That's 4 over 0.1, and that comes out to be a positive. So on the right side of that vertical asymptote, I know the graph is going to go to positive infinity. So that's telling me the behavior of the graph near the asymptote. For this question, we want to identify the coordinates of all removable discontinuities and sketch the graph of the rational function f of x equals x plus 1 over x squared plus 4x plus 3. We want to find all x-intercepts and the equation of all asymptotes. So for our function f of x equal x plus 1 over x squared plus 4x plus 3. We'll start off by looking for the location of any removable discontinuities. So I want to factor the numerator. The numerator is already factored, and factor the denominator. The denominator does factor into x and x, 3 and 1, and I'd have a plus on both of them. And now that it's in factored form, I can see that I do have a common factor, and we could reduce this function even further to become 1 over x plus 3. So because there is a common factor, we know that there is a hole in the graph, or sometimes called a removable discontinuity. So that common factor that we found is going to tell us the location of where that hole or removable discontinuity is. If I set that factor equal to 0 and solve, I know that there will be a hole in the graph at x equals -1. I can find the y-coordinate of that hole by substituting -1 into this reduced rational function. So if I substitute -1 into that reduced version, that's going to give me 1/2. So I know that the hole in the graph is going to occur at the point -1, 1/2. But then we want to sketch the graph, and as we sketch the graph, we want to find the intercepts and the asymptotes. So let's find the intercepts. I want to find a y-intercept. To find a y-intercept, I let x equal 0. F of 0 equals 0 plus 1. And I'm going to go ahead and use, instead of using the original function, I'm going to use the reduced one because I should get the same values. That's 1 over 0 plus 3. That's 1/3. So I have a y-intercept at 0, 1/3. And then when I look for x-intercepts, I'm going to let y equal 0. So I'm going to set my whole function equal to 0. And you want to make sure you use the reduced one, because otherwise you will get an x-intercept that doesn't exist if you use the original function. So make sure you use the reduced. And if I try to solve this, I would clear the denominator by multiplying by x plus 3. That gives me 0 equals 1. And that's a false statement. I don't get any solutions from solving this equation, so there are no x-intercepts. So I found a y-intercept and no x-intercepts. Then I want to find my asymptotes. We have vertical asymptotes and horizontal asymptotes. So looking for vertical asymptotes, I want to make sure my function doesn't have any common factors, and I already took care of that. And once there aren't any common factors, I would set the denominator equal to 0 and solve. Get x equals -3 as the location of the vertical asymptote. Then I want to look for horizontal asymptotes. And for horizontal asymptotes, you want to look at the degree of the numerator. The degree of the numerator is 0 because there's no variable. The degree of the denominator is 1 because we have a highest power of 1 being on our variable x. And because the degree of the numerator is less than the degree of the denominator, we have the case of the horizontal asymptote being right on top of the x-axis, which is y equals 0. So now I want to use the information that I've gathered to sketch a graph of this rational function. So what we found is that we have a whole or removable discontinuity at the point -1, 1/2. And -1, 1/2 would be about right here. I'm going to draw it with an open circle. We have a y-intercept at 0, -3. I'm sorry, that's 0, 1/3. So that would be about right here. We have a vertical asymptote at x equals -3. So I will draw a vertical dashed line at x equals -3 for our vertical asymptote. We have a horizontal asymptote at y equals 0. So I'll sketch right on top of the x-axis a horizontal asymptote of y equals 0. And that's all the information I have so far. I want to find a little bit more information, particularly I would like to have a point on the left-hand side of our vertical asymptote so that I would know how to draw the graph on the left-hand side. So I would like to pick a value for x that is less than -3. For example, x equals -4. If I let x equals -4 and I substitute that into my function, that would be 1 over -4 plus 3. That's 1 over -1, which is -1. So at -4, I get -1. So as I plotted that last point, I just noticed a mistake that I made in plotting the y-intercept and that whole or removable discontinuity. So if we take a look at the ordered pair for the y-intercept, it's 0 and +1/3, and yet I drew that point for the y-intercept below the x-axis. So I've plotted that point in the wrong spot. So let me correct that. I'm going to erase that y-intercept and move it to be above. So that's about 1/3. I did the same thing with the hole in the graph. The removable discontinuity should have a y-coordinate of +1/2, and yet I drew it below the x-axis. So I'm going to correct that. Let's erase and draw that at -1 and +1/2 would be about right here. Let me see if I can do a better job on that. 1/3. 1/3 should be below 1/2. Okay, so I've made those corrections, and now I'm going to draw a sketch of the graph. So I'm going to focus in on that point that we plotted just a moment ago right here. That was the ordered pair, -4 with a y value of 1. And that point is sort of trapped in between this horizontal and vertical asymptote. So I'm going to draw the graph by approaching those two asymptotes. And then on the other side, I'm going to focus in on that hole in the graph as well as the y-intercept. The hole in the graph and the y-intercept will connect to each other. And then because of the vertical and horizontal asymptotes, those will guide me on how to draw the rest of the graph. I want to follow those asymptotes. So from the hole, I'm going up to +infinity to approach that vertical asymptote, and from the y-intercept, I'm following the horizontal asymptote. So we have a sketch of the graph of f of x equals x plus 1 over x squared plus 4x plus 3. Thank you for checking out my videos. Have a great day.